Topic 18.1 is looking at a different definition to what categorizes an acid versus a base, and it's called Lewis acids and bases. And it is based off Lewis, the scientist who made the Lewis dot structures. And so is the same gentleman who made this broader definition. What was Lewis's theory beyond the electron dot diagrams? Well, he decided that when looking at characteristics of acids in particular, he looked beyond just the proton. He looked at actual electron donation and electron movement because, again, he did electron models, so it makes sense that's the way he went. His definition, or the Lewis acid definition, is that an acid is a lone pair of electrons acceptor, whereas a base is a lone pair electron donor. And so if you have the capability of having a lone pair of electrons, right? So let's say we go with a Bronsted-Lowry where we have a proton. And the only way a proton can go to a base traditionally is because it's positively charged. That base needs to have a lone pair of electrons. And we have talked about that with Bronsted-Lowry acids and bases. The base has to have a lone pair in order to take a proton. So the only difference is that Lewis is not looking at proton movement, he's looking at electrons. And so the base is the electron pair donor and is going to donate its electron pair to the proton. Remember from organic chemistry that it uses curly Q arrows, and that's what I drew, and it always shows the electron pair donation, right? So when we go through and put these together, then you get ammonium. With this hydrogen being the acid that accepted the lone pair from that nitrogen. So the definition of a Lewis acid is much broader than the Bronsted-Lowry definition because the Bronsted-Lowry identified an acid as anything that has a proton to donate. Lewis showed that some elements and compounds took on acidic properties because they had the capability of accepting an electron pair without ever having the hydrogen attached to it. And so that made it a lot broader. When this happens, it forms a coordinate or a covalent bond. What this looks like is for any compound that has an incomplete or empty valence shell, that it has the capability of being filled, so it doesn't have the true octet. So boron, which is typically stable with 6 valence electrons, does have an empty valence shell still, or an incomplete valence shell, sorry. And that means it has the capability of accepting an electron pair. So if we take boron trifluoride and introduce it to ammonia, well, ammonia has the capability of providing its electron pairs to complete boron's incomplete shells. And so we create a more complex compound. And we always show this in this particular instance when you're creating a coordinate bond, or also known as a dative bond. We always use an arrow pointing from the electron donor to the electron acceptor. And so that is what that coordinate bond is. And that way we understand that this is not a typical compound, but it had the capability of being formed. So that means that boron trifluoride, that is our acid because it accepted the electron pair from our base, ammonia, that had the electrons to provide. Now, transition metals are actually some of the most common elements that have acidic properties, but they don't ever really have a hydrogen attached to them, so we don't quite, like, the Bronsted-Lowry definition does not equate for the acidic properties of transition metals. Because they have or most, have a vacant D subshell somehow because there's 5 shells. And so it takes a lot to get them all filled. And so they have the capability of bonding with ligands, right? And so ligands, hopefully that kind of rings a bell, are anything that have a lone pair of electrons, like water, cyanide, or ammonia. So these are typical ligands. Kind of just need to have those memorized, and I apologize, right? And since they have a lone pair of electrons, these are going to be your Lewis base, because they're going to have the electrons that they can then donate to a metal. So an example of what this could look like. So if we have a copper ion, and why it takes on slightly acidic properties is when we put it into water, it creates a complex ion. And the reason that it does this is it actually gives off a hydrogen in addition. So there's actually a hydrogen over here that gives it its acidic properties. So that means this copper is your Lewis acid, and the water is the Lewis base because it has the electrons to provide to the copper. So these terms, hopefully you've seen from organic chemistry. We're just bringing them back again. Nucleophiles versus electrophiles. So nucleophile, nucleo means nucleus, and phile means to like. So it means it likes the nucleus. That means it's an electron-rich species, and that has an electron pair to donate. So therefore it is our Lewis base. Again, these are our ligands, and so it has to have, it has to be a compound or an atom that has an extra pair of electrons in which to donate, like a hydroxide ion, in which you've seen that hydroxide ion a lot in organic chem. You have your amine group or your ammonia that goes to amine group, again, organic chem, and you could have a halogen, and so you can make a halogen alkane, and because it has a lone pair of electrons. An electrophile, electron, phile, like. So that means it likes electrons. That means it's electron deficient, and therefore it can accept electron pairs, right? And so that's going to be anything with that vacant D sublevel. So like we've seen with boron. It doesn't matter what boron's attached to because it is stable with 6 valence electrons, right? Any transition metal or any other ion that gets formed in a certain process. So all these are just examples of electrophiles. So here we have a summary of looking at Bronsted-Lowry versus Lewis acid. Bronsted-Lowry is definitely the most common, but Lewis acid opens up a nice broader definition that helps explain acidic properties of atoms that we would not normally call acidic. So if we look at the definition of an acid, a Bronsted-Lowry is a proton donor, whereas Lewis is an electron pair acceptor. The definition of a base, Bronsted-Lowry, proton acceptor, and Lewis, electron pair donor. Those kind of go, again, I can't reiterate, these go hand in hand, all right, for the base, because in order to accept a proton, you have to have an electron pair. It's the definition of an acid that makes the Lewis theory just a little bit broader.